Okay, here's our day one of 5-1 angles in radian measure. We finally get to talk about some trig. These are some of the pictures out of the book, just the notes, and a lot of this is vocabulary that I think you should know, but probably haven't seen in a while. It has definitely not come up with anything else that we have done so far this year. So the rays of an angle, remember in one ending point and then continuing in the other end. I know that was from geometry. The vertex of an angle here in this middle one where the two rays meet, the initial side versus the terminal side is just where I'm starting and then where I'm finishing. So whenever we measure our angles, we have a start and we have a finish. And part of that is that the direction will matter as to whether it's positive or negative. In standard position, and we'll get into this more so, I think around 5-4, 5-5 maybe. Standard position just means that the vertex is at the origin. So when we think of this in our standard plane with our XY axes, and we have quadrants 1, 2, 3, and 4, the angles in standard position, if the vertex is at the origin and then the initial side is along the positive axis. And so that's what we're looking at here. Standard position where it's positive is because this angle is going up in that counterclockwise direction, and then negative whenever we start and head down instead. So we have a positive direction and a negative direction. My rainbow pen is kind of hard to see on that. So a positive direction and a negative direction. The next set, classifying by the measure of the angle, you should know everything there in figure 5.5, classifying angles by degree measurement. So at this point in time, if you need to pause to copy down the things that you don't know out of those first four, or copy everything down if that's going to help you to remember it. But this is the basic vocabulary that we'll see coming up over and over again. So we'll practice a little bit of this in the book work, but otherwise we are going to take a look at this next section. So next, making sense of what a radian is. So if we think of an arc on the circle, so not the whole circle, just a part of the circle, and what the radius of the circle is. Central angle was another one from geometry. We had central angles versus inscribed angles. Just make a quick little picture of that. Oh, look at how it makes a perfect circle. So if we have that central angle and then the inscribed angle would have been the one, it was almost perfect. And then the inscribed angle would have been the one with the vertex on the circle. So this was my inscribed angle, and this is my central angle. So that's all that it means. It is what it says it is. It's at the center of the circle. The arc length divided by the length of the radius. So like when we think of circumference, how many times can we wrap around the circle? We are looking now at the arc length, and basically if we were to take the radius and plot that around the circle, how many times does it fit? So that's what this second one looks at. 2 radians. So if this is the length of my radius here, if I take that and wrap it onto the circle one time and then a second time, that's why it has a length of 2 radians. The same thing happens here. If I take the length of my radius here and then I wrap it around to see how many times it fits in 3 times. And you can see that 3 is almost halfway there. So recognizing just what a radian is, this formula, theta is S divided by R, and then the conversion. This is going to be a big one. This should be as easy as converting feet to inches. And so like I said, from that example, that was almost halfway, and that is because pi radians, a little more than 3.14 is 180 degrees, and 180 is half of the circle. So if you can remember that relationship, that those two piece together, the pi and the 180 degrees, it's really, again, like I said, feet and inches, just which unit is top or bottom. And then that's how we would work through some of the problems here at the bottom. These are the big ideas for 5.1. So again, just kind of rewinding up to here, all this vocabulary. So knowing standard position, vertex, the start and the finish, classifying angles by their degree measure. We'll spend some more time talking about standard position later. And then all things radians. So the arc length divided by the radius, and then the important conversion that pi radians is the same thing as 180 degrees. So this problem set, we'll take a look at a couple, and then a couple of them will be on a Google form as our exit ticket. Instead of having any kind of homework or anything, I'm just going to give you less than 5 problems to take a look at that from these notes should have made sense. So in the first 6, is it acute, right, obtuse, or straight? The degree measures should be super easy to pull and recognize here, 1 through 4. So 135 degrees is more than 90 but less than 180, so that would be obtuse. Same thing with the 177. And then I have less than 90 degrees. So I have 2 acute angles here with 3 and 4. So the degree measure shouldn't be an issue. But then when we're in radians, when we're talking about pi, pi is 180. And so if you need to convert this to think of what's going on, that this is 180 degrees, then we know that that's a straight angle. And 180 divided by 2, because pi is the same thing as 180, would be 90 degrees. And so this conversion, and we'll see a lot more of this when we start talking about the unit circle, would be 190 degrees. And so this would be my right angle. Sorry, my screen keeps blipping all over the place. So classifying acute, straight, obtuse, or right should be pretty easy for us. 7 through 12, the radian measure of the central angle. So if we're trying to find the radian measure again, that was that formula up above, that theta is equal to the arc length divided by the radius. So just how many times would that fit? So for each of these, we're really just taking second column and dividing the first column. So for number 7, we would simply have that it's 40 inches divided by 10 inches, or it has a length of 4 radians. Okay, that whole set of problems is that easy. So I'm not going to waste my 15 free minutes of my video working through those. I think we can handle each of these. And then looking at a couple of conversions. So 13 through 20, we want to convert what we have and leave it in terms of pi. So we are simplifying these fractions. So for all of these, we have the degrees. And this, again, this is the dimensional analysis, my conversion of units. I need to multiply by pi divided by 180 degrees so that the degrees essentially cancel, and I'm left with my pi, which is in terms of radians. So something like number 13, I would have 45 degrees multiplied by pi divided by 180. And so if you need to use your calculator, if you want to think of this as 45 pi all over 180, you can take 45 and divide it by 180, and then math fraction to convert it back. These, again, a lot of these numbers we're going to look at are going to be the same numbers over and over again. That's equal to 1/4. I don't want 0.25 times pi. It should be rewritten as pi over 4. Instead. These are all the same. It's just a matter of how they simplify. So even something like number 20, where we see a negative 200 degrees, we still want to multiply by pi over 180 degrees. The only thing that we talk about or have to think through with that negative here is just that we're keeping it. Just keep this as the regular multiplication of fractions that you would be used to. When we think of it in terms of graphing, it's just whether we're going counterclockwise or clockwise from those pictures up above. So this was on the top right corner of the notes. So we have another measure for this angle in the positive direction, and that's something that we'll practice with later. 270 divided by 180 is 1.5. That, again, no decimal points, but that would be 3 halves. And again, the negative just hangs out, so -3/2 is all that you have to work through for that one. So 13 through 20, all of those same conversions. Now, the difference here, whenever I am working from radians to degrees instead, is that I have radians instead of degrees. And so in order for this to end up in degrees, I need my 180 in the numerator and then multiplied by pi. So where I know so many of you love to pick up your calculator, please don't. Simplify the pi first, because it will always simplify for me. So something like number 21, pi over 2, which we already looked at up above in number 6, and we recognize that should be 90 degrees. If I take my radians, my pi over 2, and multiply it by 180 over pi, these will simplify. Right now, if I have a pi in the numerator or a pi in the denominator, I should be able to just cancel those. If you need to rewrite it as 180 pi divided by 2 pi to be comfortable canceling out those pi's, then go for it. And 180 over 2 is 90 degrees. And then for each of these, the negatives are going to behave just like they did up above. So let's try one with a fraction instead, because I know we don't love to see fractions. Let's do 26. So if we have 11 pi over 6, and I'm going to multiply it by 180 over pi. Now, in my world, I would cancel those pi's. And then 11 times 180, I could do, for me, a big number, and I would use a calculator to do it. Or if I, again, recognize that these are designed to simplify, 180 is divisible by 6, because 18 divided by 6 is 3. And so 180 divided by 6 is going to be 30. So then really I'm just left with 11 times 30, which is 330 degrees. Okay, the next set of problems that are listed there all the way up to 40 are exactly the same as what we would have done, but in those you would pick up a calculator, because you would make sure that you're rounding, as it says, to 2 decimal places. So the conversion itself, though, is the same, degrees to radians and radians to degrees. It's just what your final answer format looks like. While I would love to have everything, as you know, left in terms of pi so that it's super accurate, we'll have enough practice just because questions like 13 to 20, it's going to be hard to enter pi as an answer in a Google form, that sort of thing, whereas we should be able to simplify nicely for 21 through 28. So again, that seems like an awful lot of material. What we have to do with it is not, hopefully, too involved, and that really, again, is because it's quite a bit of review, and then highlighting a couple of things here as we kick off all things trigonometry.